desk is in the campus. There we go. Okay, how are we doing? Sweet. I will try to be on time. I can't guarantee it only because I've got another class right before this one upstairs. So yeah, I mean, it's not that I'm not in the building, it's that I'm trying to work my way down. So, but fortunately for you, this is the first class I can say I don't have a class after this. So if you have any questions, you can always pin me down afterwards. So that's always good. So yeah, good. Everybody's supposed to be here. I mean, like you're not like looking for like biology or chemistry or something. Just making sure. You never know, like, right? Like, every once in a while somebody wanders in, you're like, the wrong room. Okay, cool. Yeah, okay, well, I guess we better get rolling here. So, yeah, we'll go, keep going at it. Incidentals. So I took out, I mean, at some point, I guess I should have had more, I mean, some of your faces look familiar, some of you I haven't met before. I'm Greg, Dr. Robinson, Dr. G, Homie G, Hey You, you know, whatever you want to call me. So you have my official permission to call me whatever you, well, okay, like within reason. I mean, like you can't call me like, you know, MF professor or something like that. Like, but yeah, I mean, you don't have to call me Dr. Robinson if you prefer to call me Greg. That's perfectly okay. So it's always good to, you know, when you're addressing a professor, to address them in the most formal manner possible, and until they say otherwise. Right? This is your permission to call me whatever you, again, within reason, whatever you feel comfortable calling me. So yeah, so there's that. Incidental. My office is in this building. I know that you've already done one semester of physics either here or somewhere else, but if you've done your lab stuff here, think about going up to the lab room, and I'm right next to Leo's office. So you walk down that corridor, and you have Dr. Brooks, and then you have Leo, and then they have this weird door that has a sign hanging on it, and there's some bass bumping from the other side or something. That's my office. Except, well, okay, the headphones have to get really jacked up in order to hear the bass, but, so yeah, so it's in 254, just up the stairs, take a right and you'll find me. Feel free to email me or pop by the office. If the door's shut, just hammer on it and I might be in. Sometimes I forget to flip the sign, or shamefully or not shamelessly, sometimes I'm just like, okay, I need half an hour break, and I just shut the door and I play, you know, read the news or play video games or something, right? So, but if the phone rings or if the door bangs and I'm in there and I'm not actually doing something important, then I'll stop and answer it, and then, you know, that kind of thing. If you need to set up a meeting, or if you don't like the drop in, I've got a whole bunch of sidewalk talk, so yeah, if you bang on the door, we'll probably just go outside, or we'll go into the physics lounge and work there, just because it's a little bit more open space. But if you want to, if you prefer to email me and set up a meeting, that's fine. Just go ahead and give me a couple of times I'll work for you. So instead of playing the email tag, you know, like, oh, 8 o'clock, no, I've got astronomy. Well, how about 10:40? No, I've got, you know, like, it just prevents that phone tag kind of thing going on. So email me 3 times and I'll email you back. And I can do it on Teams if you want. We can do it in person. If you'd rather just, you know, talk about physics while walking the cross-country course, that sounds pretty good to me too. So whatever your heart's desire. It'd be nice to get 5 miles in. Right, you want to go right now? We don't have to run. I mean, it can be 14, 15-minute miles just walking. Get a nice brisk pace going. No? Okay, so let's see. Yeah, most of the stuff that has to do with the course, it'll just be on Moodle. So, and by that I mean, okay, well, I have a PowerPoint slide deck. I'll try to post stuff to Moodle at the end of the week from the PowerPoints. I mean, I guess I could upload the master slides right now, but I'm still editing them. So, I mean, I could give you all 200 slides, but chances are by the time we get to slide 20, I'm gonna already be changing stuff. So, but at the end of the week, I'll try to make sure that I get those posted so that you have what we talked about for the week. I've got a little writing pad, so if something comes up when we do something by hand, there'll be, you know, handwritten stuff, and so that's the other reason, is that sometimes it's nice to have the handwritten stuff as well. So, but yeah, if it's anything that's digital, at some point it should make its way to Moodle. That includes the fact that I'm recording this lecture. I think I'm recording this lecture now that I think about it. Sorry, let me double check to make sure I'm actually, okay, no, I am recording, okay. sorry, Ben, I tend to wander as well, so I'm all over the place. So that includes like, there's a stream recording going on, so I'll try to post that to Moodle once I, get back to I'm gonna go to lunch after this, and then I'm probably gonna go to my office and I'll try to get these linked into Moodle, so then you can click on them later and see it, hopefully within the day. But yeah, so there's that, same thing. Syllabus is posted on Moodle. Anything that's digitized will get up on Moodle at some point. I've tried to organize it a little bit differently. Historically, I've done it by weeks, but sometimes, I mean, it kind of feels goofy the more I was thinking about it, because some of our topics are going to extend like, 2 weeks or sometimes 3, depending on how long it takes. So I was like, well, so I'm trying it in topics instead. Instead of going week by week, I just said, okay, topic, forces and charges, and then electric field and circuits. And so I did it a little bit differently. If that's not your cup of tea, or if it's not working, I can always change it back. It's just, it'll take a little time to click and drag stuff back to the new locations. So let me know if that's kind of, like I said, I'm trying it out. If that's not working, let me know and I'll switch it back. So yeah, okay. So now if I can find everything and stay in frame and all that kind of stuff. So yes, this is a screenshot of the astronomy one, but I guess I could pull up the real one. I assume everybody's at least familiar with Moodle. Used to, okay, you know how to access it. It's not like 3 weeks are going to go by before you say, hey, Greg, where's my homework posted? All right, just making sure. So yeah, again, contact information up here. Notice there's no N in the middle. So if you email robinson@hanover.edu, I will not respond. Sorry, it's nothing personal. It's just that it never got to me. Okay. So there's that. Every once in a while, and you've seen this already, I'll send out a bulk email to the class via the Moodle server. Do not hit reply. To the best of my knowledge, if like you got, I think I sent you a bulk email yesterday. Now that I think about it, is that right? And it says something like, from Moodle. It says in the address line or something that's from Moodle. If you hit reply to that, I don't receive it. So, so if you really need to get a hold of me for some reason, open up Outlook, type in my name or let it autocomplete and then send it that way. So, but contact information, like I said, open door by appointment. Ty is the tutor. It's just they haven't established the tutor center hours yet. So by all means, use that resource. Of course, you've got me as well, but Ty is particularly friendly. And if you're not giving him a hard time during the semester, then something's wrong. Okay, so you should be going and giving him a hard time and maybe ask him some physics questions every once in a while. Okay. And then ask him some really ridiculous physics question, like, yeah, how do you calculate the space-time curvature of the Minkowski in space or something? Yeah. And let him chew on that. If you need some more problems, I mean, just let me know and I'll just try to seed some for you. I don't know, by the way. Okay. So syllabus has been posted. My apologies. Yeah, it's some other issues. That's okay. So the syllabus is here. I would say particularly, I tried to hash it down so that it's not like at one point it was a 10-page slog, and I said, screw that. We're going to try to hack it down to just the bare essentials. So there's grade points. I think I set a 12-point grade scaling on there, rounded to the nearest 10th. There's exams, 3 exams and a final. There's a schedule in there. There's the page of if academic assistance, academic dishonesty, physical health, mental health. So there's all that stuff in there as well. But you need to take a minute, take a couple minutes of your time, sometime between now and Friday. Look over that. Yes, I know when you go from 10 pages to 4, there's going to be some stuff that's sacrificed partially just to make it look a manageable size and increase readability. So if you have a question on something, please feel free to ask. It's not for better or for worse. But the philosophy is, my philosophy has shifted from making this an all-encompassing document to trying to give you a good overview of what's going on the important points. Okay. So I got tired of, something would happen and then I would have to add an extra line to the syllabus, and then something would happen, I would add an extra line, and eventually you get a 10-page syllabus, which feels more like a legal document. And, okay, that's not what it's supposed to be. So the last 2 pages have a schedule. Okay. I will try to stick to that schedule, but if you've heard rumors about me, I'm sometimes long-winded and get stuck on certain things. So I'll try my best to stay on that schedule. The idea being, let me see if I can open that up, if I can find my mouse, good gravy. So, pull this up, yeah. Okay, blah, 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 blah. So the last 2 pages have some sort of schedule where I try to give you some idea of the topic that I'm going to be discussing. I've tried to indicate some reading sections in here. And then usually on the submission one, the lecture homeworks or the homeworks associated with lecture, I will try my best to make sure that they're due every Monday. Okay, so if we fall behind by a little bit, then yes, that means I have to go into Moodle and reorganize the due dates. And that happens. I think the only time that that's not happened, I think I think it's winter break where we have Monday, Tuesday off, and so I think I make it due on Wednesday. So just because I'm like, okay, probably if you have questions about it, and I'm here, but I don't know if you're going to be here. So if you have questions about it, but I think I make that one due on Wednesday only because you have a break on Monday. So, but other than that, yeah, just think every Monday, and if we fall behind in the lecture material, well, then it's still going to be on a Monday. It just might be a week away. Okay, so that's what I try to do, just to make sure that we have some sort of regular schedule with it. Outside of that, I've got exams posted on week 4. I think the second one's on week 8, and then the next one's on week 12. I would prefer not to move those, only because I know that you're trying to set a schedule for yourself as well. So I don't want you thinking, oh yeah, I've got an exam on week 4, and then I walk in on week 3 and say, well, we're a week behind, so we'll just shift the exam. No. Although that, from a practical standpoint, that would probably be easier in terms of lumping the content together in the right exams. But I don't think that's fair for you to be prepared for an exam on week 4 and then me walk in and change it on you. So, so however far we get is what the exam will cover. Okay. So I'll just adjust the material on the exam to match how far we've gotten in the class. So yeah. So hopefully we'll have charges, we'll have the electric field, the change in potential and capacitors, and then we'll keep going. My goal is to get through charges, to get through magnets, to get through circuits, to get through light. So we've got, if you were thinking of this whole class as if you wanted in 4, kind of 4 steps, we're going to get charges and then circuits and then magnets and then light. That's the order that's going to go in. And charges would be everything from how do charges talk to each other? How do we find the forces between charges? How can we manipulate these things? And probably everybody's favorite, how can we stop using vectors? Okay, I see some nodding. Okay, so yes, there's some painful stuff because, I mean, we're going to have to deal with vectors for a little while, and I'm going to have to ask you exactly, since I didn't have you last term, I'm going to have to ask you exactly how far along we are on vectors and try to figure that out. But one of the advantages to going through and setting up some of this framework is eventually you can stop using the vectors. And that's what the, actually, shoot, I guess I should ask. I assume, I mean, I assume we've got some chemists, I assume we've got some biologists. I mean, pre-meds, I don't know, so okay. Sorry, I missed the chemists, I guess. Okay. So I'm just curious. I mean, you see that V, this capital V that I have in here, the electric potential comes into play a lot in biology and chemistry. So if you're talking about the, biology, this would be the potential difference of the cell membrane, for example. That would be a V, and that ties into these charges things. Or if you're talking about a chemical reaction, you're usually talking about electron volts in terms of energy. Is that right? EV. Okay, that V is volts, and that's the same V that you see here. Okay, and we'll get into the fun things about, like, for example, magnetism. Eventually, we should get to the point where something like your mass spectrometer, which I know chemistry uses it, I don't know if biology does, but something like the mass spectrometer, you should, at the end of the class, have some idea about how a mass spectrometer works in terms of filtering out things. You can get some of the physical basis for that operation here, and I'll work on the biology. If you come up with some good biological example, let me know. My PhD work was in biophysics, and I still don't understand how to incorporate biology and physics. Like, so okay, yeah. The cell membrane is a dielectric filled capacitor. Okay, so moving on. So, okay, yeah, so please take a look at that. And then, like I said, I'll try to stick to that as best I can. Eventually, we'll get into light. You might say that seems like a funky kind of, a funky connection going from charges and magnets into light. It's a really interesting happenstance at the later half of the 19th century was the discovery that actually these electric fields and these magnetic fields are exactly what light is. So this, if you really wanted to, a shameless plug, if you're ever interested in modern physics, next semester, right, Phys 225, I'll see you there. You don't want to know about light? No. How about the speed of, how about time dilation?
No, it's okay.
But everybody does movies on it. No, so it turns out that the, yes, it turns out that the study of the electric and charges and magnets leads into a better understanding of what light actually is. And then you keep going into 1905 with special relativity and Einstein, where you get those, yeah, like I said, time dilation and all those cool movie plots and that kind of thing. So anyway. Okay, so take some time to look at that. Questions so far? Yes.
So for exams, you said it like takes a certain amount of days, like on syllabus, you talked about it being multiple days.
Yeah. So I figure what I'm gonna do. So, well, and again, we'll have to, I'm trying it out for a second term and we'll see how you like it or not like it. But what I figured I was gonna do, since I did it last term and it didn't seem too bad, what I'll do is I'll program it all in Moodle, and then it will open on a Wednesday, and so it'll be available, say, Wednesday, and it will close, I can't remember, did I say Saturday or Sunday? I don't remember, I'll have to go back and look out to be, part of the reason I write this up is because I can't remember, and so then I have to go back and reference it myself. But let's say it's a Wednesday to a Sunday. So it's available between those days. Now, when you open it, a clock will start running, say 2 hours. So you have any time between Wednesday and Sunday to actually open it and take it. But once you open it, there's a 2-hour clock running in the background. And it's not like, oh, you open it, you shut down the browser. No. The clock runs on the server. So the server says, oh, Greg has access to the exam, start keeping track of the time. So like shutting down or, exiting out won't do anything, and the clock is still running even though you've turned off the browser. So we'll try that. And then I think I've got the problem sorted out because I was having problems with uploading images. I think Riley has set me straight on how to get that right. So you should even be able to typing up this stuff is not encouraged whatsoever, but if you could write it out and then just take a screenshot and upload it, take it with your camera and upload it, or if you have a scanner or that kind of thing. So we'll see. And like I said, if it bombs terribly, then I didn't get a 100% this is terrible last term. I didn't get resounding success either. It just seemed okay. So I figured I'd try it again and see what happens. So it gives me a little bit more flexibility. And also makes it easier to read some people's writings. If it's just a paragraph question and you just write out an answer, sometimes it makes it easier to read your responses. So we'll try it out. Yeah.
When we start doing exams, could you let us know the times that you're most available at so we can kind of.
Yeah.
If we have questions.
Yeah, I mean, I'll say right now, Monday, Wednesday, and Friday mornings. First of all, my schedule, I've put it on the Outlook calendar, and I believe that if you access your email through the Hanover stuff, I believe you can see whether I'm available or not. I have to double check that. But I've programmed all my courses into the calendar, so I think there's a way for you to view what my calendar looks like. You just can't tell what I'm actually doing. So it'll say that I'm busy from 8 o'clock to 9:10. Now it's a lecture for me, but from your side, you'll just see Greg busy. I'll see if I can find some instructions for that, but I thought that that's possible. But Thursdays, I tend to be free. Fridays and Wednesday, Monday, Wednesday, Friday mornings, I'm completely busy until noon. So I've got 3 classes. This is the last one. So if I come in and I'm looking frazzled, it's because 2 classes went terrible and I'm looking for a repeat. No, that's not nice. Okay. Thursdays tend to be the optimal one. Of course, once you get into the weekends, I'm pretty hit or miss, partially because I don't know what Graham and Nora are doing. But on the other hand, I'm like 50 feet away. So if I look at my email and there's something that absolutely needs taken care of, then I can get into my office pretty quickly. It's just a matter of getting in front of the computer. Oh. I'm in the yellow house, by the way. So if I catch you guys hot dogging around the point, I'm going to egg your car. Okay, no. If I catch you hot dogging around the point, hanging out the window, I'm going to take the hose out. Let Graham go at it. No? Water balloons? Okay. Yeah. Yeah. Thursdays are probably the best. Other questions? Where is this camera at? I swear. Okay, there we are. I've never played with this thing. It's just too technology fangled. Yes?
Are the exams open now or closed now?
I cannot, how do I say this? Technically, they're open note, open book, open everything. Because if I said it's an honor system closed note, that only hurts the honest people. And I know that's all of you, right? Like, I mean, like, I'm talking about the one friend that took the class 10 years ago. No, I mean, the issue is if I played it by the honor system, that only hurts the honest people, which isn't fair. So the only way for me to really, the only way to be consistent with everybody is to just, it's a free for all. That being said, I reserve the right to randomize numbers and or questions. So, yeah. So yes, it is possible that you might not have the same question as your friend, maybe. Other questions? I also, it's similar to the exams, I also have the homeworks posted online. So aside from, no, that's not the right button. What is going on here? Okay, let's get that out of the way. Personally, I think that this upcoming events thing is probably the best on the right-hand side over here. I think I have stuff opening, but it lists the close dates. So if you're having trouble, you know, that upcoming thing, I think is probably the easiest, just to look at it and say, okay, I've got this coming up in a week or 2 weeks. It also displays on my calendar, you're probably aware. But the homework assignments I also have programmed in already. So theoretically speaking, oh, that's not how to get there. Let me find it. Theoretically speaking, you know, you can click on this and it should already be open. With the homework assignments, I've set it up. I think that it's, you have 2 attempts at it. Okay, so bear with me, it's a bit of a structure, but you have 2 attempts at it. Does it say 2? Oh no, it says highest grade. So I guess apparently you have them limited. That's fine. That's how it is. Why is this? Okay, while this is chewing on it. So the issue is you have attempts at it, and you can take multiple attempts. Within a single attempt, say it's your first attempt, okay, it will, you get your 10 questions or however many there are. You can take multiple attempts at each question within the entire homework set. Okay? So you can do an unlimited number of homework sets, and inside a single homework set, you have multiple attempts at the question. Every attempt at the question will deduct 10%. Okay. So you open up the entire homework set, you start doing question 1, and it takes you 3 times to get it right. You get a 70% for question 1. You know, question 2 through 10, you get 100%, and then it'll do the entire score. Okay. You say, drats, I can do better. That's fine. Open up a second homework set and everything resets. Okay. Which means you open up the second homework set, you can do everything, you get 100%, boom, you're gonna get 100% on that homework. Because it'll take the highest of the attempts. Okay. So within a given attempt, it will deduct 10% every time you do a question. On a per question basis. So you say 60, say Greg gets a 60%, and he says, oh, I can do better. You can reopen it, and if you truly understand the stuff, right, the numbers will change, but if you truly understand what your issues were and how to go at the problems, then you can get a higher score the second time. Yeah. So I know there's like a bunch of flexibility, right? Multiple homework sets and multiple homework attempts and, you know, multiple attempts on each question. So there's that. Yes, but that being said, if you do a second attempt, the numbers will change. Some of them won't. I mean, there's some multiple choice questions or some free responses, you know, that kind of thing. But other ones that have numbers in them, some of those numbers will change. So if you really know what's going on, then it shouldn't matter that the numbers change. Oh yeah, there we go. Yeah, so yeah, I've tried out some free response stuff as well. I would encourage you, I mean, my personal opinion, I would encourage you to type it out like in a Word program and then just copy and paste it over. But you could also just type it in directly here if you want. The only reason I say that is because then you know, if something goes sideways, you still have a copy of what you wrote, so then you can just paste it back in. Or if you do a second attempt, you don't have to retype everything in, you can just copy and paste it in. Yeah. Presuming it's right. So there's that. Questions so far on that? It does accept units. So if I ask you for, you know, what's the gravitational force on Greg's keys, and you do mg, you know, you calculate out the value and you forget to put newtons at the end, it will count it wrong. All right. So be careful. Okay? Don't forget the unit. It'll say the answer is wrong. You could have the number right, but if you don't put the units in, it'll still count it wrong. All right. What do you mean? Is it 10 joules? Is it 10 newtons? Is it 10 meters? Units are important. Right? What is it? Air can Gimli glider. Units are important. Right. I think it's Gimli glider. Air Canada flight. It was when Canada was transitioning from the imperial to the metric system, and the guy filling up the plane did a bad calculation. He thought that the numbers were in. Let's see. He thought the numbers were in kilograms, and it turns out they were in pounds. So he thought that you had 100 kilograms, for example, 100 kilograms of fuel. He actually only had 100 pounds of fuel. Incidentally, they were halfway across flying Canada and they ran out of fuel. No, units are important. Don't worry, everybody landed. It was okay. It was good. They landed on an abandoned racetrack. So it was like it was the Miracle on the Hudson for Canada, right? Granted, the pilot got in trouble because he didn't check the calculations. He should have known that he only had half as much fuel. But then he also got an accommodation for actually saving the plane. So it's like making your own mess and then solving your own mess, and you know. Okay. Yeah. I mean, the other one, I mean, more pertinent would be something like, don't confuse milliliters with, you know, they're oftentimes, okay, so this goes into biology, but oftentimes you see them pop up every once in a while where somebody doesn't convert millimeters properly into like cubic centimeters. And so then you end up giving bad drug dosages because you misconvert. The one that I know of is, I think it was Dennis Quaid's twins somebody did a bad conversion from like millimeters to cubic centimeters and gave a dose of something that was like 1,000 times larger than they should have. So don't worry, everybody's fine. That's the only reason I talk about such stories. But yeah, be careful, units are important. I know something, it's been gone through, I think this is the 3rd class that I've used them in, but if something goes sideways or something seems goofy, like, no, this really does seem bad, like there's some, I think that my first pass, I'm probably 80% effective at programming, and it's been used twice since then, so I think we've got most of the errors, most of the kind of weird things, but let me know if something seems sideways. So. Anyway, okay, so that's that. Yeah, so you should be able to open it up and, you know, there's free response, there's click and drags, you know, that kind of thing. And then here, you know, you have numeric. Okay. Same thing, you know, yeah, okay, multiple choice, you have some pictures, yada, yada, yada. So, yeah. No, back out of that. Nobody wants to see me get anything wrong. There we go. You know, there we go. Questions? Yes.
So for the free response,
Mm-hmm.
Once we submit the homework, we're just gonna have to wait for you to kind of grade it?
Yeah, I'm gonna have to go in and grade it. Yeah, yeah. So hopefully, been trying to, I mean, you know, like you new year, you're like, okay, new habit. So like get up at 5 and answer emails before the day starts, you know, like, so this would be one of those is like, okay, Monday night, grade homeworks, and free response stuff. Hopefully keep up with it. Yeah, yeah. It should give you feedback on the other questions. It's just, it won't give you a total score until I actually get those graded.
Okay.
So, yeah. Yes.
Is it all right to work on the homework with classmates?
I view okay, so there's a couple of things. Well, yeah, the short answer is yes. Okay. Now, the analogy I use is something like this. Imagine that you and a friend are traveling from Indianapolis to Miami. Okay, it's, I don't know, some non-COVID winter break thing. So you say, okay, well now, of course, you and your friend, you live in different parts of Indianapolis, and you're going to meet at the hotel in Miami. Okay? So it's okay to sit there and plan, you know, when you're going to arrive, and maybe even if you meet up for lunch or something like that. Okay. What it's not okay to do is make sure that you're driving side by side the whole way. So that's the gist. Yes, it's okay to work with. In fact, your fellow classmates are probably your best resources, because as they're trying to explain something to you, they're going to start learning it better too. Okay. When you ask questions of each other, you'll find that the person that knows a little bit will actually learn a little bit. The person that might be a little weaker in a particular area starts learning stuff a little bit. So it's beneficial both for the person that's doing the explanation, but also, you know, you try and, hey, you've done really good, but right here's the thing that looks a little goofy. Okay, so that's okay. What is not okay is if you drive side by side the whole way. Okay, and okay, so the example I'll say is, oh yeah, quick. Okay, this literally happened to me once. If you have to use a variable for an angle, what variable would you use? Just out of curiosity.
Theta.
Okay, theta. Yeah. I don't know, anybody have some personal, I mean, this is a personal preference, right? Like I tend to use theta or phi. Okay, I don't know what your personal preferences are. Like, I mean, theta, phi, alpha, beta. Okay. So this happened once. Okay. There was a homework problem that had an angle. They had to do it in terms of variables, and there was an angle in there. Okay. And I walked into the class and I said, what's your favorite angle? And literally everybody said theta or phi. Okay. And I said, well, that's weird. How come 50% of you use chi as the angle? I couldn't even, I had to look it up. I didn't even know what chi looked like. I had to actually look up the name of the thing because I didn't know what it was. Okay. And I got a silent response. And I said, there's only one person in this world that I know of who uses chi as an angle. You know who it was? The person who wrote up the solution manual for the book. Okay. You're driving side by side to Miami. That's too much. Okay. So that's what I mean. Okay. And I mean, I'm just giving you this example because at that point, I can't tell you exactly where the line is, but I can definitely tell when somebody's crossed it. Okay. So if you think that you're relying a little too much on your neighbor, that's the good time to say, you know what, I'm going to go and take a couple hours and just try to hack this out myself, because there's some value in the struggle as well. What it really should be is that you've worked on it, your neighbor has worked on it, and then you come together and you discuss points where you're getting stuck on. Hey, I was stuck on this. Like, what's going on there? You go, oh yeah, I see. You've mistaken the distance between. You've mistaken this distance for that distance. I mean, sometimes it's as simple as that. Sometimes there's something deeper, but yeah, that's the kind of the discussion that has to happen. But you have to put your honest effort in first. And the same thing, you come to me and knock on my door, I have no problem showing you how to do a homework problem. But I'll first ask you what you did. Hey, explain to me what you did. Explain to me how far you got. How did you start the problem? Where'd you get stuck at? You know, those kind of things. So if you haven't done that beforehand, then I'm going to say, well, why don't you go and work that out for half an hour and see first. I don't know where to start isn't a good answer either. Okay. Yeah, you got to make some sort of attempt at it first. I don't know if that helps or not. Yeah. If I see copy and pasted paragraphs that look the same. Oh, and incidentally, when you use big fancy words, I probably shouldn't say this, but when you use big fancy words in your paragraphs, it immediately says that you copied it from somewhere. I mean, most of the time, I mean, like that, you know, right, like, oh, the homological morphism of the space-time metric tensor. What are you talking about? Right? I'm gonna take that thing, I'm gonna put it into Google, and I'm gonna see if Wikipedia comes up with it. I shouldn't tell you that, right? But at this point, we know, like, you know, these are the things. We know when something looks wrong. Not 100% of the time. Yeah, I should say that. Scare you. I've had other horror stories. Yeah. No. Turns out one time I had a class where 1,000 divided by 100 was 100. Incidentally, 18 out of 24 people did that mistake. Guess where I found that mistake? In the solution manual. So, yeah, anyway. Okay, that's it. Scare you? No? Okay. Other questions? Okay, good. I'll take this off the screen. Let's move on to something else. Okay, so let's make sure textbook, yeah, I got it. Syllabus, I got it. Homework, I got it. Lecture notes. Okay, I said something about that. Extra credit. Yeah, I didn't. I'll go back and check, and I'll email you because I didn't see it when I had the Moodle screen up. There is a pre-course survey and a post-course survey. And I'll go upstairs after this and make sure that it's visible and say, hey, it's available. But that is your extra credit opportunity for the class. And it consists of a series of questions which you may or may not know the answer to. That is fine. I'm just asking for your best attempt at it. Then after 13 weeks, you will be asked a post-course survey of questions. Theoretically, you will know more of the answers. And essentially what that is used for is not to assess you, but rather it's to see if there are topics or if there are particular concepts in the class that I need to spend more time on. So I'm kind of using you as a gauge of what material did I accidentally skip over that I shouldn't have skipped, if that makes any sense. Or what material did I go over or did I omit that I shouldn't have omitted? That's one way for me to figure out where that material is. So I will email you because, again, I apologize. I didn't see it displayed when I was looking at the Moodle page. I will email you to let you know that that's available. The big thing is that you get extra credit for doing both of them. So if you want extra credit in week 13, you got to do this part in week 1 because it doesn't do me, the data doesn't, I can't use the data if I don't have both. So I will give you extra credit, but I have to have both. So yeah, I'll make sure that that's visible for you. And I think I have that shutting off sometime on Sunday. I think it was Sunday. I'll go back and double check it. Again, it's not meant to be like a stress. Again, I want to see your best effort, but it's not meant to be like this, you know, it's low stakes, it's not supposed to be anything too arduous, but just to see kind of where you stand or ideas that you might have. So. Okay. I think that's all that I have to say about that. Is that everything? Yeah, structure. Okay. Yeah. So yeah, so there's always a good question here. This is my opportunity to, you know, I haven't had everybody in the class yet. So this is my opportunity. Like, what do you guys remember from 6 weeks ago, or maybe longer? No, it was like 6 weeks, right? But it feels like an eternity. Okay. I mean, like, what do you remember about how is physics arranged? What's the structure of physics? Ideas that you talked about previously? Heck, if you have to just throw up vocabulary words.
Vectors. Yeah.
Okay, so yeah, so you have vectors. Okay, so I agree. Yeah, you got, okay, well, if I could actually find, where did it go? Oh, there it is. Yeah, so you have something like vectors. Okay. Of course, those in themselves are not physics, but that helps us discuss some of these physical quantities that we run into in the mechanics section of the text. So, we'll use that as a segue. Can you think of physical quantities that were represented by vectors?
Direction and magnitude.
Okay, so a vector would consist of a direction and magnitude. Good gravy, why does it keep disappearing? There we are. So this would be a direction. Oh, man, this is so hard to write like this. Let me go like this. There, direction and the magnitude. What else do you, I mean, so again, that's describing the vectors themselves. Yeah.
Force and velocity.
Okay, so you have, so that's what I mean by some physical vectors, right? Right now, this is a mathematical kind of idea. You have an arrow, it points in a direction, it has a length, but we associate physical quantities with some vectors, like a force, like a velocity. You want to know how fast an object is moving and in which direction. Okay. So that's what I mean by some physical quantities. So we have things like, man, I don't understand why it keeps disappearing. So you have something like velocity. I'll put forces down here. You have force. Okay, keep going. Let's jog some memories. I mean, okay, so discussion-wise, what do you remember about forces? I mean, what were some like 30,000 foot overview of forces? I mean, what do you do with them? How do you describe them? I mean, okay, that's the big one usually, right? You're dealing with forces I mean, that's what I mean by 30,000. I'm not thinking about the little details, like you're probably thinking, okay, you've got ramps and you got pulleys and you've got things flying through the air, and I'm thinking larger than that. Like you're faced with a force problem, a problem that deals with forces. Usually, one of the places you end up going is F equals ma, Newton's second law, right? You look at the net force acting on your system, and you can relate it to the acceleration of that system. Vector notation, is this okay? Okay. I tend to write arrows over it. Yeah, I mean like arrows. If I'm dealing with the magnitude, just to let you know, I will try to write the vector and then I'll put absolute signs around it. Okay. Some books, it depends on, era and the book that you're using. Some books will just simply write it as V without the vector sign, and it's up to the reader to realize that it's a magnitude. I don't like that only because then it's a matter of, if you write that on an exam, it's hard for me to know whether you thought that it was a vector and meant to take the magnitude, or if you just completely forgot that it was a vector in the first place. So I tend to prefer something like this, where you indicate that it is a vector, and then you say, hey, I'm taking the magnitude of it. Now, yes, I will also fall into this trap where I forget to put, when I'm talking about magnitude, and I'll forget to put the absolute sign. Okay, yell at me, try my best. Yeah. Okay, so what else do we have? I mean, okay, so when we're dealing with forces, you tend to think about Newton's second law. You tend to write F equals ma. You would identify forces acting on your system. And incidentally, what you put over here, what you put in this F net, I mean, it depends on the situation, right? If you have a falling object, maybe it's the force of gravity. Or maybe if you have an object that's sliding down a ramp, it might be the gravitational force, and there might be some frictional force in there. Or, I don't know, I'm trying to think of things. But I mean, like, this is kind of the starting point, and then you tailor this equation to match the situation you're faced with. What else you got? I mean, what are some other kind of overview ideas, kind of starting points when you're dealing with some of these problems?
Energy and momentum.
Energy and momentum, right? At some point, usually what you end up doing is you start off with this projectile motions, thinking about velocity, and really that's kind of to get you used to vectors, I think. Then you go to forces, and then after that you go to energy. So, okay, so energy is a nice, now what's one of the advantages that energy has over forces? I mean, that's not, okay, there's a G there. Just curious. I mean, you could probably name a lot of them. Let me ask you this, quick. Is energy a vector or a scalar? It's a scalar. Right. Who wants to deal with vectors their entire life? Oh, nuts. Okay. So one of the advantages that energy provides, it gives you a different way of looking at some things. Energy is very good for answering some questions. For example, how fast are my keys going to be moving when they hit the floor? Rather than having to worry about vectors, I can do this all in terms of energy and get a scalar value. And in fact, this is 1D, so that's not too bad regardless. If you use forces, it's 1D, and so it's not bad. If you use energy, it's a scalar, so it's not bad. But where it starts getting a little more hairy is if you do something like this. Right? Now it's a whole lot easier to do it in terms of scalars, energy, than vectors. Because now I'm doing 2D. If I want to do vectors, I've got to do two equations. I've got to worry about the x direction and the y direction, and I got to, sub and solve and blah, 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 blah. Or you could just do energy and be done. So one of the advantages here is that this is a scalar. Let's put scalar here. Sorry, must have the mapping wrong today. Yeah. So what kind of forms of energy do we have? What kind of forms of energy did you talk about?
Potential energy.
Okay, so you had potential energy. What kind of potential energy? Incidentally, notice I'm trying to figure out how far you guys were and what you talk about. Elastic. Okay. Or I don't know. Did you use elastic? I can't remember if we used elastic or we call it elastic. Did you call it elastic potential energy? Okay. And what do you associate with that? How do you know if an object has some elastic potential energy? What's the observable? How can you point to an object and say that must have some stored elastic potential energy? If it's a spring or something, yeah, I agree. If it's a spring or something, what do you notice specifically about the spring? Okay, so it's, yeah,
It's a state of rest.
It's a state of rest, okay. Well, how do you know, does this have some elastic potential energy? Yeah. If it were at its state of rest, what should it look like? What have I done to store some potential energy in this guy versus this guy? What did I do?
Trap some air in there.
I trapped some air in there, but what did the balloon do? It stretched. It deformed. Right? Elastic, like can stretch. Right. This has some stored, so I'll say it's deformed. Somehow you've changed the shape of the object, the energy. Could I get this energy back out? Yeah, what do I have to do? Pop it. I just clip the end here, and if I clip the end and let go, what's this balloon going to do? It's going to take that stored elastic potential energy, and it's going to convert it back into kinetic energy. Right? And just start flying around. So usually we associate some stored elastic potential energy with the deformation of the object. Now, of course, I'm using a balloon here, but a spring would be the same. You take a spring and you compress it from its natural length, and now I've changed its shape. It's got some energy stored in it. I let it go, boom, it's going to pop back out. Trampoline, same thing, right? Nothing on it. No stored potential energy, it's flat. Somebody bounces on it, you change the shape. And so it's stored, and then it'll pop it back into the person or maybe your knee or something. What other forms of potential energy do we have? Yeah, we have gravitational. How do we, what's the observable associated with gravitational potential energy? Just curious. How do you know that an object has gravity? Okay, I'll put little g here. So spring. How do you know if an object has gravitational potential energy? Oh, shoot. Is it? I don't understand how to get this thing to track me. Follow me! Hey, Siri. Okay, whatever. How do you know if an object has gravitational potential energy?
If it has height compared to the zero line.
Yeah. We'll say something like distance above Earth's surface, or you could probably go a little further and say separation between yeah, but I'll take it, yeah. I mean, you could say, well, right now, yes, it's got some stored potential energy, it's some height above my reference point. And like going, okay, yeah. So I'll say the distance, the separation between two objects, I'll put it that way, that's pretty generic. Yeah. What are other forms? And you may or may not have talked about them in class. I don't know. You can feel free to pull from other areas, right? I mean, I'm sure that some of you have P-Chem in your future, so you're going to be talking about other forms of energy. And maybe I shouldn't say you don't have to make it potential energy anymore. I mean, what other forms of energy do you have? You have kinetic, motion of an object. Oh, I'm sorry. What's the observable? Yeah, if it's moving. If you observe it moving, then it must have kinetic energy. Okay, right. So all these energies we try to associate with some observable. So the motion of the object. What other forms of energy do you have? Thermal. What is thermal energy?
What's the type of kinetic energy?
It's a type of, so we have macroscopic kinetic energy, right? An object, a large object moving across the room. Someday I'm going to break my keys, okay? But you also have microscopic kinetic energy, right? The motion of the individual atoms which the keys are comprised of. I've changed, when we usually say kinetic energy, we're talking about the macroscopic motion. If you're talking about the microscopic motion, we usually think about thermal energy. And incidentally, thermal, what's the observable? Not quite heat. I like where you're going with it. How do you know if Greg's cup of coffee has increased in thermal energy? Change in temperature, right? The observable is the temperature, the change in temperature. Incidentally, oh, yes. So we got, okay. I'll come back to that heat comment in this. Actually, we'll do it right now. What do we call the process when we transfer energy from the surroundings into the system? Well, the thermal, okay, that's the, yeah, that's the P-Chem thing coming in, isn't it?
Endothermic.
I'm sorry?
Endothermic.
Oh man, that's the chemistry thing. Okay, yeah, let's see. Oh shoot. Yeah, so if energy flows from the system into, or excuse me, from the surroundings into the system, yes, that would be an endothermic reaction. Yeah. But from the physics standpoint, okay, so yeah, we got chemistry now. Work. Work is the process by which you take energy from the surroundings and you put it into the system. For example, let's take the system as these keys. To increase their kinetic energy, I must somehow transfer energy from Greg into these things. That process of energy transfer on the macroscopic scale, we call work. Greg applies a force on the keys through a particular displacement, and that is giving the keys some energy, which manifests itself as a change in velocity, a change in kinetic energy. They start moving. How about if I wanted to do this on the microscope? That work is the macroscopic one. This goes a little bit beyond 161, that's okay. So if you're familiar with this, great. If you're saying what's going on, don't worry about it. But if I want to microscopically transfer energy from my surroundings to my system, let's say heating up my cup of coffee on a stove. What do we call that microscopic transfer of energy? Where my stove, which is made of atoms, start vibrating really quickly, and those vibrating atoms hit the water, and because of that collision process, the water starts vibrating more quickly. What do we call that transfer? What do you think it might be called? No, it's a time you've actually used it already. Not thermodynamics, it's the other one you gave me. Oh, you don't remember that? Oh, does anybody else remember it? Heat. So you can think of macroscopic work. You're taking energy from the surroundings and putting it into the system. Greg throwing the keys. Sometimes heat is referred to as microscopic work. It's looking at the individual atoms and the collision between atoms in the surroundings with atoms in the system to transfer energy. So Greg's cup of coffee that's slowly cooling off, you would talk about heat transfer. There is energy being removed from my system into the surroundings, the coffee. And I know that energy is being transferred because what happens to the observable, the temperature of the coffee? It decreases, the temperature goes down. That means the thermal energy of my coffee goes down. Well, that energy had to go somewhere. The cup of coffee's not moving macroscopically, but microscopically, those atoms are moving slower. Well, where is that energy going? It's through the collision process with atoms in the air. So that's the whole basis of thermodynamics. It's taking care of where is the energy. You have macroscopic work, you have microscopic work, and the combination of those two gives you the change in energy of your system. Now, we didn't deal with heat, right? We didn't do that on 161. Okay. We won't do that on 185. If you get really jazzed about that, you go into, what is it, PChem? Yeah, you take PChem 1, or is it 2? Is there a second PChem?
There's quantum mechanics.
Quantum mechanics, yeah! Do that one too, okay? Yeah, so there's like PChem where you start talking about thermodynamics. That's 100% talking about energy right now. And quantum mechanics, that's, you get jazzed about light, and then you take modern physics, and then you can go into quantum mechanics. You guys don't. Modern physics is awesome. I don't know. I mean, okay. Okay, so we've got, yeah, things like thermal energy, you've got kinetic energy. You could probably say something like chemical energy, right? There's energy associated with the bonds between atoms. And you can get that energy back out by breaking those bonds. That would be something like not endothermic, but exothermic, right? You probably deal with this every day, right? You take, shoot, what is it? It's been so long since I've had chemistry, I'm sorry. You take a bunch of, you take something like a bunch of bonds between oxygen, carbons, and hydrogens, and you break them apart. Was it C6H12O6? Is that right? Otherwise known as glucose, right? That's stored energy. That's stored energy in terms of chemical. And what do you do to get that energy back out? I think, right? Am I completely bogus here? Like, you guys are the ones that, I have never had a college level biology class. Okay? So I expect you guys to like correct me when I say something wrong. And if I say something right, you got to nod, okay? So it's like, yeah, C6H12O6, glucose, and how do you get that stored energy out? You break the bonds, right? I mean, am I smoking something on this? Right? Like, I'm right? Like, you break the bonds, and that's how your body, that's how you get the energy back out. Okay, you stored it in chemical energy, chemical potential energy, and how to get it back out is you break the bonds. Okay. Yeah, ADP to ATP. It's the same thing, right? ADP. What does ADP stand for? Diphosphate and triphosphate. And I can't remember. That's part of the conversion cycle? Is it plants that do that? Oh, is that, you see, there's my biology limit. I'm like, that's animals, right? Plants, maybe? Okay, yeah, like ADP to ATP. What's going on? Well, to create ATP, you force the phosphate to combine with ADP, is that right? Through a proton pump? Right, there's a gradient, and it, like, the proton goes in and it turns the motor and it smashes an extra phosphate onto the ADP to cause ATP. You're basically taking the motion of the hydrogen through the cell membrane and creating a chemical bond. So if you want to get that energy back out, you just break ATP and turn it into ADP and you get the energy back out. Right? Okay. You got to tell me if I say something wrong because I'm really out of my zone. Okay. Like this is, that's my physics perspective of it. Right? Okay. So you can store energy this way as well. Of course, chemical energy is a little harder to figure out how much energy is stored there. Okay, usually you do a very sophisticated experiment, right? You take this chemical potential energy, say this marshmallow, you stick it in a calorimeter and you just burn the sucker, right? You just light it on fire and see how much energy it gives off, right? Calorimetry, is this right? Right? Take a marshmallow, stick it in a calorimeter. You surround it with water that's at some temperature. You burn the marshmallow and you record the temperature increase of the water. You say, well, the temperature increase of the water must correspond to the energy given off when I burn the marshmallow. That's how much energy must be stored in the marshmallow. And then you go to the box of Lucky Charms and you say, this marshmallow has 200 calories of energy. And that goes on the box. No? Maybe? I mean, it's more sophisticated than that, but that's the basic idea, right? Okay, thank you. Score one for Greg.
Dietary calories are kilocalories.
Yeah. There's the dietary calories are kilocalories, which, it's like 1 calorie is 4.138 joules, and I got really confused when I was in France. Kilojoules, what the heck is going on here? Like, I don't know what's going on anymore. Okay, so that's the energy part. How about, it was also mentioned momentum, right? So then you get something like momentum over here. So this allows you to deal with, up until momentum, you essentially deal, by and large, you're dealing with a single object. Okay? You're dealing with a box sliding down a ramp or a ball flying through the air. Okay? When you get to momentum, you're now allowed to start thinking about multiple objects. Right? What happens when ball 1 collides with ball 2? And okay, so but the point I should probably make here is that you're doing a lot of the same stuff. What really dictates which thing that you choose is what information do you start off with, and what are you asked to find? If you are asked to find the time it takes for the keys to fly from one side of the room to the other, you generally have to start thinking about something like forces. Right, because energy, if you go back and think about energy, nowhere do you actually deal with time. Right, usually you have to come back here to accelerations. Acceleration has a time in it. Now, if you want to know how fast an object is moving, generally energy is a better way to go. Because you could get it with forces, but you have to do it with the vectors and a couple equations, and again, depending on what the problem is. Whereas energy gives you a faster way of going at it. So momentum, again, it highly situational. Anything else? I mean, what else did we talk about in physics?
Kinematics.
We had kinematics, which is a special case of Newton's laws. Oh, I should ask, kinematics, when can you apply the kinematic equations? Under what specific circumstance? The acceleration is constant. Yeah. Right. So kinematics, you can think, you spend a lot of time on kinematics, probably 2 weeks, 3 weeks on it. But in terms of, in the grand scheme of physics, it is a very special case of Newton's second law. This is constant. Yeah. What else we got? Just curious. If I have a pen and I do this, from here to here, what do we call that motion? Where we maintain the orientation of the object and we just slide it.
Linear.
Linear, okay. Well, okay, so let's do this. All right.
Is that translation?
This is translational, right? Translational motion, the orientation of the object stays the same, and we simply shift it from one location to another. Okay, now if I do it in a straight line, we'll call it linear motion. So then I'll do like a wave here. This is still translational. The orientation of the object stays the same. How do we just, good so far? What do we call this? Where the center of mass of the object stays the same, but I do this. Now, this is rotational. So you have all of these ideas developed for translational motion, and then at the very end, you say, well, we'll apply those same ideas, except instead of a translating object, we will apply them for a rotating object. So then I'll say rinse, down here we have rinse, wash, and repeat for rotation. Now, instead of forces are for translational motion. You don't do translational, you talk about torque, rotational. A torque is essentially a force that causes a rotation. Instead of linear momentum, you talk about angular momentum. Instead of displacements in meters, you start talking about angular displacements. Instead of talking about velocities, you talk about angular velocities. Yeah. And of course, instead of talking about accelerations, you talk about angular acceleration. Physicists are not that creative, right? Okay, we'll just call it angular acceleration. All right. But by and large, and hopefully you saw this a little bit, by the time you got done with 161, these last couple of chapters, maybe this last chapter, it might have felt like you just had like a whole ton of equations thrown at you in one chapter. Like if you go back and look, like this is probably like chapter 8 or 9 in your textbook. I don't know for sure, but it probably felt like there was a whole bunch of equations thrown at you. I'd say the reason it felt like that is because you're basically doing all of the other stuff but with new variables. Instead of x's, you put in thetas. Instead of velocities, you put in, you remember angular acceleration or angular velocity? Radians per second. Usually the Greek letter omega is used. Instead of translational acceleration, A, you usually talk about an angular acceleration, alpha. But if you go back and look, most of those equations are literally the same in terms of structure. They just change the variables. Is this ringing a bell? Did you even notice that? I mean, I could say quick, what's the, you okay? Okay, we got 2 minutes. Kinetic energy. The translational kinetic energy is 1/2 mv squared. For rotational kinetic energy, it's 1/2. Instead of V's, it should be omega. So I'll put omega squared here. And instead of a mass, inertia, moment of inertia. Something like that. So anywhere you see a mass, you put in a moment of inertia. Anywhere you see a velocity, you put in an omega, an angular velocity. And literally, you can almost, there's 2 equations I can think of where you don't do this. Where you can take, quick, what's the definition of momentum?
Isn't that the potential to do energy?
I'm sorry?
Isn't that the potential to do energy? Something weird.
Oh, no, it's the definition of torque, and there's another one for angular momentum that doesn't quite transfer over. Yeah. But momentum is mass times velocity. Angular momentum. Moment of inertia times omega. So it's a lot of the same equations, they just Instead of dealing with translational motion, you're doing rotational. Okay, last byline. I know sorry, I know it's a lot of review and kind of, it's part of me trying to see where you guys are on this. Okay, the last byline, a lot of the first couple of chapters of material, we're going to start off with something here, forces. And I'm going to give you a new force, a brand new force. The force between two charges, otherwise known as Coulomb's law. Okay. So a lot of the stuff that you learned here in 161 comes back into play. We're going to apply Newton's law, and the only difference is that now we have a new force that we can put in on this side. Rather than putting the gravitational force, rather than putting a spring or a frictional force, we'll put in the force between two charges. Coulomb's force, Coulomb's law. Then we'll move into this, energy, because we don't like dealing with vectors. They're a pain in the rear. It would be nice if there were some scalar quantity that we could use instead. Okay. And this is where those ideas about electric potential come in. It's a fancy way of dealing with energy. Okay. So stay tuned. Thanks for your attention. We'll pick up there on Friday. And yeah, maybe we'll do some charges and we'll, rub rabbits against glass rods and do electroscopes and all that kind of jazz. Okay. Cool beans. Sweet.